All right, so 6.4, we're going to now start to talk about logarithmic. So we call that you can graph the inverse of a function by interchanging the x and the y values in the ordered pair. So if we graph or if we make a chart, we'll say, if we use the traditional 5 values, and if I sub it in to this equation, I'm going to get 1/4, 1/2, 1, 2, and 4. Now keep in mind, for the inverse, all you got to do is switch the x and the y. So I'm still going to write them as xy points, but I'm just flipping them. So it's now 1/2, -2, 1/2, -1, 0, 1, 0, 2, 1, 4, 2. And the points get flip-flopped. And then when you graph this, what you're going to see, we have -2, 1/4, -2, 1/2, 0, 1, 1, 2, 1, 2, 3, 4. Here's 1. And then the other one, -1, 1, 0, 2, 1. What you're going to find is you have these two functions. Okay? So every exponential function has an inverse function. The inverses of exponential functions, they're called logarithmic functions. And what you're going to find is that they are reflections over the line x equals y. Reflections over the line, we'll say actually y equals x. Because y equals x goes right here. So if you were to flip one onto the other, they would match up perfectly because they're reflections of each other over that particular line. So now let's just jump into some algebra. So it says, suppose that b is greater than 0 and b does not equal 1. So for x greater than 0, there's a number y such that if we have the log base b of x equaling y, this is true if and only if and only if. What we're going to do is we're going to make a circle. So b raised to the y power equals x. So b raised to the y power is equal to x. The definition of logarithms can be used to express logarithms in exponential or logarithmic form. So if you're asked to write something in exponential form, okay, exponential form would follow that format. So this is where you have to do the circle. So we have 3 to the second is equal to 9. Here we have 10 to the -2 is equal to 1 over 100. Whereas if we go the opposite direction with logarithmic, logarithmic is this form. So what I always say is, all right, we'll set it up. You know something has to go here, you know something has to go here, and you know something has to go here. And envision what it would look like if you were to do the circle. So now you can see what to plug in. Because if it's 5 to the third, 5 is here, 3 is here, and then the 125 goes here. So your final answer would be log base 5 of 125 equals 3 for this one. So again, going to logarithmic, put all your little blanks in there so you know something has to go, and then envision what it would look like with the circle effect. And then you can see what numbers need to go where. So we have log base 27 of 3 equals 1/3. And there's our second function. All right, so now what we're going to do is, instead of rewriting it, now what we're going to do is we're actually going to solve it. So what you need to do when you do these types of questions is we have to change to exponential form. So we're going to change it to exponential form. So when we do that, what we do is we take the equation and we set it equal to x. And then we do our circle. So we have 1/2 raised to the x power equals 256. and then we want to get it into the same base. So 256 can be in terms of 2's, so can 1/2. So 1/2 is 2 to the negative 1 to the x. 256 is 2 to the 8th. So when I distribute, I get 2 to the negative x equals 2 to the 8. So negative x equals 8, which means x is negative 8. For the next one, set it equal to x, do my circle. So 3 to the x equals 243. I can get it in terms of a base 3, because 3 to the 5th is 243, which means that x is equal to 5. So part 2 to this, besides just the algebraic, is the graphing part. So when you graph a log function, again, you've got 2 instances. So in this case, though, it deals with what the base is, so what the lower number is. So if b is greater than 1, right here, then you're going to have sort of the growth appearance. It's increasing. But if b is now between 0 and 1, which means it's a fraction, you're going to have the decay appearance. So also, when you go about this, we're going to follow some of the same steps that we followed for the exponentials. So we're going to start with a graph for these. And again, what you have to try to envision is the circle every time you're doing this. So you have to say to yourself, okay, so 3 to some power is equal to my x value. So that's what you have to keep in mind. So if x is equal to 1, 3 to what power would be equal to 1? Well, that means that this has to be 0, because 3 to the 0 is 1. If I pick 3 for my x value, 3 to what power is equal to 3? Well, that would be the first, and that gives me 2 points right there. So I have 1, 0, and I have 3, 1. Okay, now, b in this case is a 3, which is greater than 1, so I'm going to give off the growth appearance, or the increasing appearance in terms of my graph. And so what you should find is you should have the upwards trend going right here. Now, your asymptote for exponentials, it was a horizontal line. For logarithmic, because they're inverses of each other, your asymptote is going to be a vertical line. Okay, so just keep that in mind. So it should not be passing, in this case, it's not going to pass the y-axis here. All right, so in terms of identifying domain and range, the other things that have to follow, we had said exponentials and logarithmics are inverses of each other. So with exponentials, the domain was always all reals, or negative infinity to positive infinity. That's now switching over to our range. So the range is always going to be negative infinity to positive infinity, whereas our domain is only going to be from 0 to positive infinity with parentheses, because it's only the positive values that are going to apply here. For b, or for letter b, the b value in this case is 1/4, which means that 1/4 is between 0 and 1, so this is giving off the decay appearance, so it should be coming down. Again, I would figure out values that are going to make your life easier to graph this if you do not have a calculator. So let's say we make x1 again. So then you say, all right, well, 1/4 to what power is equal to 1? Well, that's 0. And then if I do the same thing, let's say with, oh, actually, let's just keep it 1/4. 1/4 to what power is equal to 1/4? Well, that would be 1. So that gets me 2 points to work with, which is really all you need. Okay, and you know it's coming down, but keep in mind it can't cross that y-axis. So our domain, again, it's going from 0 to the right, so 0 to positive infinity, and our range is going to be negative infinity to positive infinity for all of them. So now the next piece that comes into play is where all this transformation stuff goes. So it says the same technique is used to transform equations of the graph you've studied. So we're going to add stuff now to it. So let me just add the general formula up here. So we have f of x equals a log base b to the x minus h plus k. So that's the standard format. For the horizontal translation, it's the opposite x value. And your asymptote now in this case is when you take the x minus h and you set it equal to 0. Your vertical translation is your y values. And in terms of a now you're reflecting it over the x-axis, not the y-axis. So just be careful with that. All right, so in terms of our graph, you've got a calculator if you want to sub it in, or what we're going to do is start to dissect it. So b is equal to 6, which is bigger than 1. So this is giving off the growth appearance. We also have an a value that's equal to 1/3, which is positive. So we're all good there. The asymptote, okay, is where you take what's in the log function, which is x, and you set it equal to 0. So the asymptote is x equals 0. So that's our y-axis right here. Doesn't cross that point. In terms of transformations, or what is occurring, so transformations, so we know what the 1/3 is not doing much, it's just shrinking it or condensing it, but we know that this -1 here is bumping the whole entire thing down 1. Okay, so originally, with most of these graphs, with the other two examples, you were seeing that they both crossed at this particular location, which was 1, 0. Same thing here, 1, 0. So now what happens is, because we're bumping the thing down, think 1, 0 was here, but now we have to bump it down 1. So we're going to have a new location. And that new point is now going to be at 1, -1. And we said that it has to give off the growth appearance when we sketch this. So we're just going to come up here. We can't cross that dotted line. And it comes up just like that. So originally, it always crossed at 1, 0. Now we're going down 1, which is going to get us at 1, -1. There's our starting point. The domain is going to be all the positives, so from 0 to infinity. And your range is going to be all of the y values that apply there. So again, you can use the calculator to give yourself a visual of it, but it's definitely helpful to come up with where the information's coming from yourself without using the graphing calculator itself. All right, so for b, we've got b is 1/3, and 1/3 is between 0 and 1. And a is also -4, so we're going to have to reflect that. So traditionally, this should be a decay, which means the graph, in terms of a decay, if you look to the front page of, or actually second page of your note, should be coming down like this. But now if we are reflecting it over the axis, okay, or over the asymptote, it's actually now going to give you this appearance. So just be careful with that. So that negative is now going to flip it over that value. Or wait, actually, go back to page 2. So it says asymptote is that, top here. If a is less than 0, the graph is reflected over the x-axis. That's my bad. So remember, x-axis goes left or right. So when we reflect this over the x-axis, you're going to now give off the growth appearance. Sorry about that. All right, so in terms of transformations, we know that, let's do asymptote first. So our asymptote, we're going to take x plus 2, set it equal to 0. We get x equals -2. So we got -2 right here. All right. For transformations, we are reflecting it over the x-axis. So reflect x-axis. The 4 in front technically stretches it. And then we're going to go left 2 units. Okay, so think, originally we would have started at 1, 0, but if we go left 1, 2 units, our new point is now going to be at -1, 0. So there's our new starting point. Now again, originally the graph should have been giving a downward appearance like this, but we're reflecting it over the x-axis, which means now our graph should be coming up like this. So just be careful. If it helps you to graph the original and then see how the reflection happens, certainly do that. Now, domain and range we know always stays -infinity to positive, and the domain is going to go anywhere from -2 to the right. So from -2 to positive infinity would be our intervals for that one. All right, last one here. So we've got b is 1/2. 1/2 is between 0 and 1. So that would give off the decay appearance. And since a is 1/4, that's greater than 0, we're still with the decay, so that doesn't change. Asymptotes, we're going to take the x plus 1, set it equal to 0, so we get -1. So x equals -1. In terms of transformations, we're going down 5, we're going left 1, and there's no reflection. Okay, so originally we would have started at 1, 0, but now we're going left 1 and down 5. 1, 2, 3, 4, 5, and there's our new starting point. 1, 2, 3, 4. So now we should be at 0, -5. And we said it was decay, so the graph should be coming down like that. Let me go with black. All right, so now in terms of domain and range still -infinity to positive, and the range, since we said our asymptote was -1, it's now going to be from -1 to +infinity for our